Concrete is the most widely used construction material for roads, dams, and towering structures that pierce the sky. Its development has continued since its discovery, driven by the persistent challenges associated with it. These emerging solutions are expected to aid the younger generations. Hi Joanna, how old are you?
I'm 8.
Oh, you're 8. Well, in your age, have you seen tall buildings?
Like malls and schools? They're so cool!
Right, well, even your home, they are made up of this, and it contains sand and large stones and even small ones. Can you see it from here?
Yes, but how do they stick together?
Well, cement binds them together. However, there is a problem with cement. Cement manufacturing contributes about 7 to 8% of the world's total annual carbon emissions. The production of cement involves the crushing and grinding of raw materials, followed by proportioning and high-temperature burning. Firing these materials requires temperatures ranging from 1,350 to 1,550 degrees Celsius. This energy-intensive process is one of the reasons why the cement industry has a high contribution to carbon dioxide emissions, producing approximately 1.5 billion metric tons of carbon dioxide in 2024.
If that's the case, how can we produce concrete without the use of cement? Is that even possible? From what I've learned from our science class, cement is one of the key components in making concrete.
Yes, it is possible. We have geopolymer concrete that doesn't use cement.
Oh, that's good! We can now eliminate the use of cement.
That's right. However, geopolymer concrete does not use cement as its binder. Instead, it uses aluminosilicate materials such as fly ash, a waste product from electric power generating plants. It undergoes a process called geopolymerization. It starts with the dissolution of fly ash, where silica and alumina are released into the mixture. These species then start to reorganize and form a three-dimensional structure of silicon-oxygen-aluminum bonds. The 3D network becomes denser and stronger, leading to the strength development of the concrete. However, geopolymer concrete is inherently brittle due to its highly cross-linked network. As a result, geopolymer concrete becomes prone to cracking. As a graduate from the university, do you have any idea how we can address this problem with geopolymer concrete, specifically with cracking?
From my undergraduate thesis, yes. This can be addressed using the microbial-induced calcium carbonate precipitation, or the MIC. And it goes this way. So when the self-healing concrete cracks, the water will seep through the cracks, activating the dormant bacterial spores. Once activated, it will metabolize the available substrate and nutrients in the concrete matrix. As a result, the bacteria induces calcium carbonate precipitation as its byproduct, hence sealing the crack.
But don't you think the concrete matrix is pretty harsh for bacterial spores to thrive? How are we going to incorporate the bacteria into the self-healing geopolymer concrete?
There's been many ways to immobilize bacteria in existing self-healing concrete research. So we take advantage of the components that's already in the concrete, such as aggregates, as carriers of bacteria, as well as the nutrients.
That's so interesting. Can you please tell me more?
We're looking into recycled concrete aggregates, or the RCA, as carrier for bacteria. The porous nature of RCA serves as protective, cost-effective vessel for microbes that repair cracks through calcite precipitation. The incorporation of bacteria in RCA also serves as its treatment through the very same mechanism used for self-healing, which is the MICP, thus addressing the concerns regarding its porous nature. Furthermore, RCA provides a protective shelter for bacteria against high pH environments and mechanical stresses. Bacterial carriers like RCA allow spores to survive for extended periods, contributing to crack healing even when the concrete is cracked at later stages.
Hello, Engineer Charles. Are you familiar with geopolymer concrete?
Countries such as Japan, China, India, Germany, and the United Kingdom, among others, are actively researching and adopting geopolymer concrete as an alternative to cement concrete. I am also contributing to the development of geopolymer concrete through ongoing research in this field.
Perfect. Today I am with Rika, who brings with her a solution to address the cracking issue with geopolymer concrete.
The microbial-induced calcium carbonate precipitation, or the MICP technology using urease-producing bacteria, can also be incorporated to geopolymer concrete to provide it with self-healing properties. Moreover, the bacteria can also be utilized to treat the recycled concrete aggregates, or the RCA, to improve their properties.
That's a great idea, Rika. A self-healing geopolymer concrete, GeopoHEALmer. I can help you in providing an advanced solution to the construction industry, especially with the use of concrete. And with that, let us take part in advancing the United Nations Sustainable Development Goals.
By promoting sustainable industrialization and fostering innovation.
By making cities safer and more resilient.
And by ensuring responsible consumption and production. Beyond innovation, let us also expand our expertise and empower the young generation. Like the American Concrete Institute, we continue to shape the future of construction, driving progress, sustainability, and excellence.